Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session on the series of video lectures on the subject of system programming with Linux. The title of today's session is File Management. Well, I'm sure that you must have gone through the open, read, write, close paradigm that we discussed in the last session. Today we are going to see how we can reposition the current file offset of an open file using lseek. We'll learn to create and delete hard and soft links. We'll learn to change the ownership of file using chown and fchown. We'll change the file mode creation mask and permissions of file. We will see how access use the permissions on a file other than the open call. I will talk about IO redirection, and then finally I will conclude with a discussion on the usage of F control. Okay, dear students, first of all, repositioning of the current file offset. Well, most of you might have used the fseek library call, using which a programmer can set the current file offset of an open file by using the file stream pointer. Similarly, if you have opened a file using the open system call and have got its file descriptor, you can use the lseek system call for the same purpose. Oh, well, this pictorial view describes how lseek works. Suppose this is a file in front of you, a linear view of the file that is having n bytes of data starting from byte position 0 to n-1. Well, dear students, if you want to move the current file offset with reference to the start of the file, you give the whence argument to lseek as this seek set. This argument is given as seek set. So this first line of code will move the current file offset to position 54 starting from the beginning. It will count 54 and take the current file offset to that location. Remember, if you are using the whence value as seek set, the offset that is given over here can't be negative. That is, you can't move the current file offset before the start of the file. Similarly, if you want to move the current file offset with reference to the present location, you use seek cur as the whence value. So this line actually move the current file offset to 54 bytes ahead or 54 bytes before its present location, depending whether you have given a plus or a minus over here. Similarly, if you want to move the current file offset with reference to the end of the file, you use seek n as the whence value. So this last line will move the current file offset to 54 bytes ahead or 54 bytes before the end of the file. Remember, it is valid to move past the end of the file and create a hole for later insertion of data in that hole. Well, since kernel version 3.1, Linux supports two additional values of whence. One is seek hole and the other is seek data. Seek hole adjusts the current file offset to the start of the next hole greater than or equal to the given offset. And the seek data adjusts the current file offset to the start of the next data region greater than or equal to the offset. Okay, let me move on to the terminal and see this concept practically. Let me do man lseek first. Well, you can see it returns a value which is written over here as off_t. Well, dear students, although it is possible to use C fundamental types like int and long for storing file offsets or the process IDs or the user IDs, but it reduces portability issues. But it creates portability issues across different Unix systems. So the single Unix specification version 3, it specifies some standard data types having names that end in this _t. If you want to check out the values, different types, I can show you using I think they are in the directory USR include x86 64 bits and types.h. I think it should be here. Well, yes, over here you can see a lot of those data types that starts with this. Please do read this header file whenever you have time. Let me fall back. Okay, so this is the main page of lseek. Let me move down. These are the different values that you can give, the different commands, seek data, seek whole. Let me move down and see the return values. Well, just should make it your habit to check out the return value of a system call whenever you are using it, so that you should know what it returns in case of failure or success. Most of the cases, system calls return a -1 on error, and in case of success they either return 0 or some positive value. And these are the possible errors that you can see. Let me show you a program lseek1.c. Well, in this sample code I'm trying to seek the standard input, this 0. I'm trying to seek descriptor 0, which is standard input or the keyboard. I'm requesting to move the file offset to 54 bytes ahead from the start. And you all know that it is an error, as you can't lseek the keyboard. So this system call will return -1 and will set the global error number variable to an appropriate value. Let's see this in action. lseek1.c ./a.out, and you see that it says it cannot seek. Let me check the return value that this process has returned to the parent, and it contains 29. So this is actually the value which this system call has placed in the global variable error number. Let me do error number. Okay. Do read this man page when you have time in detail. This shows you a long listing of the possible errors, indicating their names and the constants, and you can see the different constants and their description. Okay, so what does 29 stands for? The error number of our interest is 29. Let me use less again. These must be there in the header files. USR include ASM generic ERR number hyphen base.h. Okay, so this file contains the error number and their appropriate constants, and the error number 29 is here, ES pipe, which says illegal seek. Okay, fine. Let me see the man page of lseek again, and over here I can see this ES pipe. FD is associated with either a pipe or a socket or a FIFO which cannot be seeked, and of course we know the keyboard can also not be seeked. Okay, so I took this opportunity to tell you how you can find out what errors your system calls have returned. So far so good. Let us see another example. lseek2.c. Okay. Well, in this file, what I'm doing is I'm just deleting a file if it already exists. I'm opening this file f1.txt, and the second argument is I want to open it in read-write mode. I want to create it, and if it exists, I want to truncate all the data. And this is the mode argument 0622, which of course will be umasked with the current system value, and the permissions will be set for that file. And the final permission on the file will be mod and not of umask, whatever is the umask. Okay, then I have shown you the descriptor, and of course we all know that since this is a start, so this open call will return descriptor 3, as we know that 0, 1, 2 are reserved for std in, std out, and std error. Then I've used lseek with on this FT with a 0 over here. This will return the current position of the file offset. And then I have written 5 characters in this file, and then I have done again lseek. The location of CFO after writing ABCD is this. And then I have moved the current file offset 100 bytes ahead of the end of file. That is, I have created a hole over there. I have done that by using lseek 100 over here and seek, and that means move ahead 100 bytes from the end of the file. And then I have got the current position of the current file offset. I have printed it, and then finally again I have printed ABCDE in capital over there. Fine. So if I summarize, what I have done is I have created a file. I have written lower ABCDE over there. Then I have moved the current file offset 100 bytes ahead, and then I have again written capital ABCDE over there. And the file name, let me check out the file name. The file name is f1.txt. Let me compile this program, and let me write it. Okay, so you see, okay, let me get lseek 2.c, and let me do /a.out. Let me shrink. Okay, so you see I have opened the file. Then I have got the value of the file descriptor, which is 3. Then in the beginning the current file offset is at 0. Then I have written ABCDE, and after that the current file offset is at 5. Then I have done lseek 200 positions ahead, so the current file offset is at 105. And then finally I have written ABCDE at the end, and the current file offset is at 110. That's great. Okay, let me do ls-lf1.txt, and this is a file which is created. Clear screen, and you can see the size of this file is 110 bytes. And you can also see the permissions are read write this, because the umask of the system is 022 and the mod was 622. So we have done 622 and not of umask, which is done 600, and these are the permissions. Okay, let me cat this file, cat f1.txt, and you see it just shows the 10 characters over there. It is not showing me the whole. Let me use od octal dump command that is used to dump files in octal and other formats on f1.txt. And while this shows you the first 5 characters, then a whole of 100 bytes, and then last 5 characters. That's great. Let me quickly show you another example, and let me cat lseek 3.c. Okay, so well, over here this program is receiving a command line argument, probably the name of a file, and it is no, it is not receiving the name of the file. It is receiving a number over here, and it is converting it to integer and placing it over here. Then I am opening or creating a file with holes, and then I am writing PUCIT, string PUCIT in it, and then I am entering in a loop, and this loop runs for this much number of times. So if I have sent 3 to this program, that means I want to create 3 holes in it. So this loop will run for 3 times, and it will create a 10 bytes hole, and then it will return PUCIT, and a 10 byte hole, and it will write PUCIT in that file. So this file will contain string PUCIT, and in between each string there will be a hole of 10 bytes. Pretty fine. Let me do gcc lseek 3.c. Okay, and let me pass, let's suppose 3, because I want to create 3 holes. Let me do od, and the file name is, let me pass -c. I want to see in characters, and here we go. So this is a string PUCIT. Then we have the first hole, then again PUCIT, and the second hole, and again PUCIT, and the third hole. And if I do get files with holes, you see we have 1, 2, 3, 4. 4 strings, and in between each string we have a hole of 10 bytes. Okay, so I have quickly gone through this, and I hope you will play with these programs and write more programs so that you should be very comfortable with how to use lseek system call in your programs. Let me move back. Okay, dear students, now you know how to use a system call, and I'm sure you can use it even if you have not used it before. So please do see the man page, and after that you can easily write down a hello world program to understand the detailed usage of that system call. Okay, now let me quickly go through some of the related system calls that are related to the file management. Well, this is the rename call. This is a library call that is used to rename a file. The old name, then you give the new name. 2 arguments are passed to it, and sample code is also shown. I think you should be able to write a hello world program that will rename a file. Well, remove and unlink. Remove is a library call, and unlink is a system call that are used to delete files and directories in your system. However, remember, if a process has already opened a file which you have deleted, the file won't actually be erased until the last process holding it open closes it. Until then, it will be removed from the directory, that is, ls will not show it, but it will not be removed from the disk. Well, dear students, remember, when a file is deleted, the operating system kernel performs following 3 tasks. First, it frees the inode number associated with that file. Second, it frees all the data blocks associated with that file and adds them to the list of free blocks for later usage. And thirdly, it deletes the entry from the directory containing that file. So the metadata of the file is still there in the inode block, and the data of the file is still there in the data blocks. You just need to know how to access those blocks. Hope you will be able to at least try this on your systems. After deleting a file, try accessing the data of the file. Okay, dear students, you know about links. If you don't know about links, please go through the operating system with Linux video lecture number 21. These are the 2 APIs that are used to create the hard link and the soft links. Well, as you know that every file that exists on your system has an owner and has a group associated with it. So if you want to change the owner and the group, you can use these commands. You give the file name first, and then you give the ID of the owner and the ID of the group. And if you don't want to change the group, for example, you specify a -1 over there. And remember, only a process with super user privileges can use these functions to change any file user ID and group. Okay, so we'll talk about the effective user IDs sometime later when we will talk about processes. So lchown is similar to chown, but it does not dereference the symbolic links. Well, let me move ahead. Well, these 2 functions allow you to change the file access permissions of an existing file. So if you want to change, if you have a name of a file, you can mention the name and you can mention the mod over here. And if you have a file already opened, you can use the file descriptor over here and the mode. And the permission of that file will be changed. So this is a sample code. Please go through the man page of these calls and write down hello world programs as a proof of concept. Okay, finally umask. We all know about the umask. Umask function sets the file mode creation mask for the process and returns the previous value. Okay, so if you are comfortable with this, it's fine. Otherwise, please go through the video lectures 22 and 23, in which I have talked in detail about the permissions and the umask values. Anyway, this is the code snippet, and once you run this and this file is created, and the resulting permission on this will be 0633 and not of 077, and that will be, of course, I think 600. That means read write permissions for owner and no permissions for group and others. Okay, fine. Let's talk about access as well. Well, the access system call determines whether the calling process has access permission to a file or not. And it can also check for file existence as well. You give the file name as the first argument, and next is the mode, and this mode argument is a bit mask consisting of one or more of the permissions shown over here. If you want to check out whether you have read permission on a file, you write this mode over here. If you want to test for write permission, you can use this. And the point to be noted over here is that open system call performs its successes based on the effective user ID and effective group ID, while access system call base its test on the real UID and GID. We'll talk about effective UIDs and GIDs in our later session, inshallah, when we will talk about process management. Okay, so we have sample codes. Let me run this program access for you. Let me get access.c. Okay, so what I'm doing over here is, okay, fine. This program is receiving the file name as command line argument, and over here I'm just checking whether this program has whether this file exists or not. This f_ok means I'm just checking for the existence of the file. So if the file exists, access will return 0, and this will be printed, otherwise this will be printed. Similarly, over here, I'm checking for the read permissions, whether on this file, this program has read permissions or not. If I have read permissions, access will return 0, and this line will be printed, otherwise this line will be printed. Similarly, I can check for write permissions, execute permissions, and whatever. So let me compile this program, gcc access.c, and let me run it on let's suppose /passwd, the famous file on which I must be having read permission. So this file exists and I have read access to this file, and of course I do not have write and execute permission on this file. Okay, let me run it on shadow file, and of course this file exists and I do not have any sort of permission on this file because I am Arif and this is owned by root. Let me run it on executable usr bin and okay, passwd, and of course the file exists and I have read access to this file. I do not have write access to this file, and of course I have execute permissions on this file. Let me do ls-l as well, usr bin password, and you see I'm others for this file. I have read and execute permission. I have read and I have execute permission on this file. And let me check for the existence of the file as well. And since this no file does not exist, so it is saying that this file do not exist. Well, there are the other programs which you should go through. The truncate, umask, and umask1 and umask2, just for the proof of concept. Okay, so dear students, let us change gear now and see how we can do IO redirection from within a C program. And before I talk about IO redirection, let me discuss a basic usage of the dup call. The dup call takes the fd as an argument, open file descriptor, and returns a new descriptor that refers to the same open file. For example, if this is a PPFDT of a process and it has 0, 1, 2, 3 descriptors pointing to std in, std out, and std error, and suppose I have opened a file at descriptor 3, and later on I call dup with a 3 over here, it will return me 4, and now both 3 and 4 are pointing to this file. And remember, the new descriptor that dup return is guaranteed to be the lowest unused file descriptor. Okay, so let me come up over here, clear screen, and see I have a program dup.c. Well, in this sample program, I have opened a file abc.txt, and we know that it will get descriptor 3. fd1 will contain 3. Then I have used the dup call to get a duplicate of this descriptor fd1, that is 3, and of course it will be 4. Now both the descriptors fd1 and fd2 are pointing to the same entry in the system-wide file table. They both will be pointing to the same entry in the system-wide file table. So the current file offset is shared, remember. So if I try to read using fd1, the same file will be read, and if I read using fd2, the same file will be read. The point which I want to highlight over here is that I am reading this file, 5 characters of this file, and then I'm writing them on stdout. And then I am again reading the same file but using fd2, and I'm writing it on stdout. And then again I'm reading from fd1, and then I'm writing it out. Okay, let me do gcc. Its name is dup.c. Yes. And let me show you the cat program as well, the ABC file as well. Okay, so ABC file contains just the alphabets A to Z. You see, this has read the 5, 510, 515, initial 15 characters from that file. And the point which I want to highlight is both these fd1 and fd2 are pointing to the same entry in the system-wide file table. And the current file offset resides in the system-wide file table. So that is why when I read using fd1, the current file offset changes. And when I read using fd2, the same current file offset changes. And that is why I have been able to read it, the first 15 characters. Okay, let me again make a minor changes program to make you have a very clear concept of this idea which I am discussing right now. Let me copy this program to temp.c. Let me vim temp.c, and let me do what? Let me open the same file twice, and let me paste them in fd1 and fd2. Okay, so in this case, now this fd1 will contain, of course, 3, and this will contain 4. And they both will be pointing to 2 different entries in the system-wide file table. And of course, the system-wide file table will be looking at the same file, abc.txt. So in this case, now, once I will compile and run this program, fd1 will have a separate current file offset, and fd2 will have a separate current file offset. Let's see the behavior of this program now. You see, once I read using fd1, A, B, C, D, E, these 5 characters were read. And then this program read using fd2, and again A, B, C, D, E is there. And then when I read using fd1 again, I have F, G, H, I, J. I hope this point is clear to you. If it is not, I strongly recommend that you should make certain changes in this program and rerun it, so that you should have a very clear idea of that current file offset resides in the system-wide file table. And if you use dup call to create a duplicate file descriptor of the same file, there will be one entry in the system-wide file table. And if you open the same file twice, there will be two entries in the system-wide file table. Okay, let us move back on the slides again. And now that we have a fair idea as to how DUP system call works, let us have a quick recap about the concept of IO redirection as well. Okay. Well, if I run the cat command, which I have shown over here, without any argument on the shell, its PPFDT will look something like this. It will read its input from the keyboard and send its output to the display device, and this process will continue until the user presses the end of file character. Let me show this to you. Let me do cat. Learning is fun with Arif. And you see, the cat program is reading its input from the keyboard and writing its output to the std out, and I press Ctrl D, which is the end of file character, and it quits. Fine. Okay, now consider this command. Over here, the descriptor 0 of the cat command has been redirected to a file named f1.txt. The descriptor 1 has been redirected to f2.txt. And this symbol 2 greater than &1 is read as, please make descriptor 2 a copy of descriptor 1. Make descriptor 2 a copy of descriptor 1. So both 1 and 2 are pointing to F2. Now a $100 question. Dear students, when cat program runs like this, how many command line arguments are passed to this? How many command line arguments? 1, 2, 3, 4, 5. Some people will say there are 5 command line arguments. Some will say no, 1, 2, and 3. And some will say maybe 1 and 2. What is the correct answer? Well, I will say no command line argument is passed to cat. And let me prove it. And to prove this concept, I have written a program, listargs.c. Let's move on the terminal and see this. Listargs.c. Okay, so this is a very simple program which is doing what? Which is just receiving the command line arguments, running the loop, and displaying the command line arguments. We have seen this program before as well. And let me say again, learning is fun with, and let me put a double quote over here. Okay, fine. This is the total command line arguments are 6. 1, 2, 3, 4, 5, and 6. And this 1, this 2, this 3, this 4, this 5. And they are displayed over here. Fine. And what if I run it something like this, ./a.out, and do this. I do the input redirection to listargs.c, the source of this file. The output is given to a file, let's suppose output. And let me do cat output. And you see the total number of arguments are 1. That is argv sub 0 contains ./a.out, and that is it. This, and this, and this. None of these are passed to a.out as command line argument. So the conclusion is the shell does not pass the redirection symbol and the file name to the command. Another important point that you should keep in mind is the redirection request can appear anywhere in the command and does not require spaces around the redirection symbol. Let me prove this as well. And let me say, okay, put it something like this and do something like this. It will work also, fine. And let me do cat output, and this is the same output. Let us fall back to the slides. Uh, so on the shell command line, we do IO and error redirection using the three symbols, this 0 less than, 1 greater than, and 2 greater than. And inside a C program, the same effect can be achieved using the dup system call. Okay. So we already have seen the dup call. Over here, I just want to rephrase the same statement that I've said before, that dup call guarantees that the new descriptor return will be the lowest unused file descriptor. So if you run this line of code which is shown in front of you, you know the open call over here will return 3. The dup call will return the lowest unused descriptor, and since we have closed the 0 descriptor over here, so it will be 0. So finally, after these 3 lines of code will execute, descriptor 0 will be pointing to the open file which has been opened over here instead of the std in. Some people use dup2 call, which makes this code simpler, and it always ensures that we get the file descriptor we want, which we have closed over here. So dup2 call takes 2 arguments. One is the old argument and the other is your request. Whatever argument you want to, whatever descriptor you want that should be pointing to the same file which this file descriptor is pointing, you pass that descriptor over here. So on the previous slide, the 2 calls close and dup can be simplified to one call, that is dup2 ft0. Let me move ahead. And we have the dup3 call as well, which is passed an additional flags argument, and that can be used to set or reset the flags of the new descriptor. And one of the flag probably we have discussed is the close on exec flag, which is there in the PPFDT of every process. Okay. Let me talk about the input redirection and show you an example. Well, to do input redirection, you first close the descriptor 0 as I have shown over here. And after that, when you open a file, whenever you open a file after this, you get the lowest unused file descriptor, and that is, of course, 0. So after these 2 lines, if you do reading on FD, this file will be read. That is, this file will be connected to descriptor 0. So instead of reading the keyboard, this program will read this file. This is input redirection. Let us confirm this on the terminal by seeing the program. Okay, let me use this program. Okay. So, well, over here you can see I have created a buffer line, and then I've used fgetS to read from keyboard 100 characters and place them in this line variable, and then I have printed that line. Fine. After this, I have closed descriptor 0. I have opened a file. So this open call will return 0 in this FD. And when I will do fgetS, and we know fgetS by default reads from std in, that is descriptor 0, which is now pointing to this file. So this time this fgetS will not read from keyboard, but rather will read from this file, and you will get the output of the first line of this file over here. Well, let me gcc std in redirect1.c. Let me do cat as well so that you can see the program while I'm running it. Okay, so right now this fgetS is asking me to enter a line. And the line is learning is fun with Arif. And once I will press enter, it will print this line. It will close 0, it will open this file, and if it will again ask fgetS. But this time the program will not halt at fgetS, rather fgetS will read about 100 characters from this line and will display them on std out. Great. Let's fall back to slides again. Well, this method 1 will not work if you have already opened a file. If you have opened a file before and later you want to do an input redirection, this method will not work. In that case, this is the method you should choose. So if you have an open file, suppose this is again 3, you close the 0 descriptor and then you call the the dup call on this FD, and it will return a duplicate descriptor, the first unused, the lowest unused descriptor, and that will be 0. So this way as well, the behavior will be same as we have seen above. So after these 4 lines of code, when the program reads from descriptor 0, the file password will be read. Let me just do get std in redir2.c. So over here now you can see I have done what? I have used the open call, then I have closed it, then I have used the dup call, and the rest of the things are same. So over here I will get input from the keyboard, fgetS will get input from the keyboard, and over here the fgetS will get input from std in, that is descriptor 0, and the descriptor 0 is pointing to this file. Let me do gcc std in redir2.c ./a.out. Fine, that is great. Hope you have understood this. And one last thing, this is the same as method 2, but this time I'm using dup2. So you see we have over here open close dup close, this is the sequence, and over here we have just open dup2 close. That is, this close and dup are combined in one call. So instead of close 0 and dup fd2, I have just used dup fd2, and I have passed its 2 arguments, fd and 0. Okay, so dear students, if you have understood this, in the same fashion you can do the output as well as the error redirection within your programs. Let me move ahead. So before I close, let me quickly talk about the famous fcontrol system call as well. Okay, let me first tell you what all we can do with fcontrol system call. Suppose we have an open file using the open system call, and the connection between the process and the file on disk is shown in this illustration on the slide. Okay, so while using fcontrol, you can perform a lot of operations on this connection, which is starting from the PPFDT entry 3 to this 54 and to this inode 233 and to these file blocks. And the operations that you can perform on this connection using fcontrol are: you can get a duplicate file descriptor of this 3, like the way you have done it using dup and dup2. You can get or set the file descriptor flags in this. Over here you can get or set this flag, and we know one of the flags that is closed on exec. You can get or set the file status flags in the system-wide file table. Like, and you can see the file access modes, that is read or read write or write only, and you can check for the file operating mode flags as well. For example, the append flag, the sync flag, and the non-blocking flag. And finally, fcontrol can also be used to achieve logs on open file. Well, the first argument to fcontrol is fd, which is actually the file descriptor, representing the connection whose attributes we want to get or set. And then the second is the argument. Second argument is the command, which is an integer value that determines the operation we want to perform on it. And the third optional argument is a long value, which depends on the second argument. Let's move ahead and see some examples to practically understand this concept. Okay, so in order to duplicate a file descriptor, you can use fcontrol command, and in that case the second argument that you pass to fcontrol over here is fdup fd. Suppose you have a file, this file open in read mode, and you want to get a duplicate file descriptor. You pass fdup fd over here, and the third argument is a number, and the fcontrol will try to get you the lowest available file descriptor greater than or equal to this argument. So it is always better to place a 0 over here, but I have placed 54. So most probably the 54 will be empty and you will get a 54 in this RV. Anyway, so F control can be used to duplicate a file descriptor. Please go through this example, which is available on my Bitbucket account. Finally, you can get the file access modes flags as well. You use the fgetfl command over here. And after you get this fgetfl command over here in F control, the F control returns an integer flags value, and later on you can bitwise and this flag with the OACC mode constant, and you will get whether the file has read permissions, write permissions, or read-write permissions. Please go through this code to have a proof of concept of this. Okay, then you can also set the file operating mode flag. One of the flag is O_append flag, and you might be knowing that O_append flag is used to ensure that each call to write implicitly includes an lseek to the end of the file. Moreover, the kernel combines lseek and write into an atomic operation if you have used this flag. Suppose you wanted to use this flag, but you forgot to set this flag while making the open system call. So what you're going to do is, you're going to use fgetfl over here. F control will return the flags, and then you will bitwise OR this with O_append constant. You get the setting, you modify the setting, and then you set them back using fsetfl over here and the flags value over here. And the way you can set the O_append flag, similarly you can set the O_sync flag as well in the same fashion. Okay, so the last thing I want to do with F control is to acquire, release, and test for the existence of file locks or record locks. For review's sake, there are two types of locking mechanisms, advisory and mandatory. And the default locking mechanism on Linux is advisory, in which processes needs to cooperate, that is, need to check themselves whether the file they are opening is logged by some other process or not. And of course, we have two types of advisory locks, the read locks and the write locks. And if you want to use F control for this purpose, the third argument to F lock over here will be a structure of F lock type. Let's move on to the terminal and see a sample code that tries to achieve an exclusive advisory lock on our file. Let me clear screen. Let me first see the man page of F control. Let me move down and see the structure F lock, which we have not discussed on the slides. Okay, so you can see this F lock structure has these values, the type of the lock you want to acquire, read, write, or you want to unlock, the events value, which has the same interpretation as we have done in the lseek command and lseek system call. Then we have lstart and len. These two values are interpreted with the events value. And then finally we need to have the PID of the process in this member of the F lock structure. So let me show you the code of this fcntl lock.c. Okay. So I am opening a file in write-only mode. I am creating a F lock structure, and the type of the lock is write lock, events is seek set, start is 0, len is 0. So it will lock the entire file. Len is equal to 0 means I am locking the entire file. This is basically the end of file. And get PID function is used to get the ID of the process. And then I'm going to call F control, and I'm going to pass it 3 arguments. The first is the FD of the file which I want to log. Then I want to set the lock, and this is the F lock structure I'm going to pass it. And of course, if I'm successful in achieving this lock, this line will be printed. Let me do gcc fcontrol lock.c ./a.out, and you see the file is successfully locked. Well, dear students, remember, if some other process tries to open this file, kernel will not prevent it, as this is an advisory lock. However, other processes can check before opening this file whether it is locked by some other process, and they can do that using the fcontrol call. If you want to ensure that when this process has locked this file, no other process should be able to open it for reading or writing. So for that case, you need to implement the mandatory locks. Well, I'm leaving the implementation of mandatory locks as an assignment. Hope you will be able to do it. Let me move back to the slides, quit this program. Okay, so that is all for today's session. In the next session, we will try writing the famous ls utility, inshallah. And that will give the long listing of directory contents. Hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time, and until then, happy learning and Allah Hafiz.